Yeah. So I think this week we're starting off with contextuality properly. So I want to give a little bit of motivation. So if you so you've taken a classical mechanics course? Okay. So I will just use some concepts there a little bit freely. Not too much, but the idea is that a state of the system, some lambda, is equal to, Q and P. I mean, there could be many of these. It doesn't matter for our specific purposes. So this is, what we would might call like an ontic state. And the observables are going to be things that are like A equals A of lambda. So this is, and these are just functions on my state space, which is very nice. So if I have something like a preparation, let's say, which is a distribution over these lambdas, then if I want the probability, say, that this observable takes value lowercase a, then this is integral d lambda. Let's call it rho of lambda, and then a squiggle, and I'll define this in a second, where I'm defining a response function, which is precisely like, it gives me 1 if a of lambda equals a, and 0 otherwise. Right? So we see that this is going to give us the probability that we want. This is a probability over all lambdas, and this is just going to give me it's going to give a value of 1 for all lambdas where this condition holds. So this is the full probability. But in fact, this is quite similar to the sort of response functions that showed up in Fine's theorem. In fact, if we consider observables, say A1 to AN, well, the probability of A1 equaling A1 all the way to AN equaling AN is precisely lambda rho of lambda, and then we have a product of these things. So I equals 1 to n, a tilde, ai lambda. Was it clear that this should give the probability that we want in the first place?
I mean,
this one.
Okay. Yes. So I guess in terms of like measure theory,
Yeah.
notation, this would be the integral over the pre-image of A, right?
Yes. Yeah. No. Hold on. I think that that's close to correct. You're looking for yes. This is the probability over. Yeah. You're looking precisely at all the. You have all the lambdas which give A. So you're looking at the pre-image of this function, right? Yeah. So this is the measure associated with that. Very good. So if I just want the probability of all these things, what do? I just sort of stack these on top of another. And this is, in fact, precisely the sort of thing that we do in Fine's theorem. We define this joint distribution exactly like this. But this is what we would have done in classical mechanics. So this sort of motivates this kind of and although we never talk about it in classical mechanics, these observables could be quite different from each other, like angular momentum, linear momentum, energy. And even though classical mechanics doesn't put any restrictions on what you could measure together, it might be that an actual experimental setup never allows you to measure all these observables together. You think of an electron, you want to measure its linear momentum, say. It goes through a uniform magnetic field, and then it gets deflected by some amount, and then you measure the radius. Well, I mean, that will give you something about its linear momentum, but maybe you will not be able to probe other properties of that electron by going through the magnetic field, right? So even though in classical mechanics we don't say anything about operational restrictions, nonetheless there might be, but we still can define a joint probability distribution. So what we do want to say is we want to sort of informally say something about what this notion entails. So let's say that what is a non-contextual value So I will write, we'll make all of this precise, but just to give a flavor, it's assignment of predetermined values to a set of observables independent of the process of measurement. Independent of so it's a good idea to just recall that we've already encountered this before when we did CHSH, so let's just remind what is going on in that case. Here, I'm going to change the notation just a little bit, but you recall that we had these sort of empirical probabilities that were obtained by having some quantum operators AX tensor I and I tensor BY, and I associated some values 0, 1, or plus or minus 1 to each of these. But so in CHSH, the non-contextual value assignments are when I do this for all x and y. That is, even though AX, these could be, by X I mean A0 and A1, and these could be just two different non-orthogonal sort of bases for a single qubit, I'm still going to assign a value to them regardless. So that's how it was in the CHSH scenario. So let's sort of work up from that. So measurement scenarios more broadly, they don't all have to be of this form. So what do I mean by that? So So I think that there's a natural way to define multipartite scenarios going based off the CHSH scenario. But what we're going to see is that in our discussion of contextuality, this idea that you have to have the operators in this sort of like very specific form with the tensor decomposition is not necessary. So in a multipartite setting, you might imagine a similar sort of situation with A1 tensor, I tensor, all the way to n possible, for n possible parties. And then you maybe have I tensor, A2 tensor, I. And you define a set of observables for each party. I tensor AN. So there's a couple of properties that we do want to abstract from. What is it about these that are very useful for us? So first is that we have that the observables pairwise commute. And what I'm saying is, when I mean abstract from this, is what is it about a scenario like the CHSH or these multipartite scenarios that we might want to continue modeling for other types of scenarios? Here we have that there's, in principle, for each qubit, maybe a different, or each tensor factor, there's maybe different operators you could look at, but for each context, each sort of measurement setting, you pick one operator on each tensor factor. And these observables will always pairwise commute. And two, you also have that they satisfy the measurement statistics. So let me say that. Are non-signaling. So this situation is not strictly necessary, but we can still sort of try and capture these two in a more general setting. So just consider observables A1 to AN. Not these, just any observables A1 to AN, and have it be that they pairwise commute for every I, j, equal, or maybe I less than j, 1 to n. So they pairwise commute. This is really what we want to look at. Instead, so this is a special case of this. This is one example of a context. So one set of observables for which you can get some measurement statistics. But it's completely valid to also do this. Let's see how that works. In principle, for each I equals 1 to n, we know that if these Hermitian operators pairwise, whenever they commute, they share a set of eigenvectors. So I can write AI is equal to the sum j, I'll call it, of A. So these are the eigenvalues for operator I. We sum over its eigenvalues j. And pi is the projector onto that eigenspace. So this is just the spectral decomposition. So this is to I put this in quotes. I mean, we just Yes, so what I mean by this is a projector. It squares to itself, and these are pairwise orthogonal, so that for different j's, you have that pi j prime is 0. It projects onto this eigenvalue in the sense that if I have any psi that's in this projection, then AI applied to that will give me this value. So we have that since the AI's commute, we can define the following. Pi of j1 to jn equals pi j1 1 pi jn n. I'm just taking one of these projectors from each of the different measurements I have here, from each of these A's, and I'm just taking their product. This will be guaranteed to, they don't have inconsistent products. They will all map to a common eigenspace. Is that okay? Because they're not necessarily rank 1, right?
But so I'm wondering, is it possible to find like a representation so that these correspond to these like, tensor products?
You are asking if it's possible to find A1 to AN. Oh, is it always possible to put them in this form? Ooh. Oh no, hold on. That sounds like so the Cyrilson problem was not like this exactly. That was a somewhat, but it's sounds like it's what you're asking is something related to the Cyrilson problem.
Let's say that these are all finite dimensional.
Finite dimensional?
Then does that work?
Are you asking if, okay, so I can have operators like this. I did not specify the Hilbert space, right? In fact, the Hilbert space could be not necessarily amenable to having a tensor decomposition. It's got to be of a certain dimension, right, for that to hold. So, I mean, it could be the case, very well be the case that there's operators like this that you can't write as in this tensor factor way.
But I mean, do you have to go to infinite dimension to have that failure? Or
Why infinite dimensions? No, I don't think that that's the case. No, because I'm just saying, okay, say that these are Hermitians acting on H, and H could be just C to some power D, and say D is prime. If D is prime, then what I understood you to be asking is from A1 to AN, can I think of these as being put into this form where they're sort of, I think you're asking, is there a unitary which maps these to something like this? Within the same Hilbert space?
well, I mean, it could be not necessarily unitary, but like a partial. So I mean, so you have like n Hermitian matrices or
Yeah.
operator, and then these form an algebra, I guess. Well, I mean, these can generate an algebra.
Is there an example that you have in mind? Is there a reason that you're wondering about this?
Well, I mean, I'm just wondering because, well, because there should be an advantage to going like to this more general setting.
Ah, I see. So I can't answer your question directly, but I don't believe it's possible to always write these operators like this. I mean, we will encounter a couple of cases where it's not clear that you would be able to make this decomposition. Yeah, no, there are definitely examples where you can't interpret it in terms of a multipartite setting. Yes, in fact, I mean, one of the, so I used to work at Bilkent, and there's a famous non-contextuality inequality called the KCBS, Kryachko, Can, Binijioğlu, and the last person's gonna hate me, but KCBS, you can use a single spin one particle for this. So you don't have to have a multipartite sort of setup, just a single quantum system with d equals 3, level 3. And so you can witness contextuality without having to deal with this multipartite setting, which is advantageous because we're not going to get into it in this course, but I am sort of interested in studying it a little more, like the loopholes. Like there will be some loopholes in terms of these multipartite settings. There's also loopholes in the other way too, but what you will not have to worry about whether the parties are sufficiently far apart, because here you actually have to have like systems of like photons or something that are actually far apart to justify saying that they're non-signaling. Like when you violate the CHSH inequalities, you want to be able to say that you are not violating the assumptions, which is namely that they're spacelike separated. So there's these loopholes. If you have these sort of contextuality setups, sometimes you can avoid certain loopholes. And there are definitely examples where you don't need to be in this setting. You can just, there's a practical advantage in this. So this is going to give me a projection onto the joint eigenspace of all of these operators. And so this is going to be my joint outcome. And so, you know, if I given a quantum state, we can, of course, define the probability of this outcome occurring to be trace, and it depends on rho, of course, trace rho, pi j1, 1, pi j n, n. Okay, so these are pairwise commuting. Does this version, does non-signaling hold? It's not obvious what that means, but I will define what it means in a second. What we really want, and if you recall from this sort of what we looked at with Fine's theorem, if you have a sort of classical model, the way that you get non-signaling is precisely because the marginals of a joint probability distribution will always agree on their overlaps. So we will also have that in this setting, there's a version of non-signaling that happens. For example, say that we want to marginalize over J1. We want to show that this probability does not, okay, actually, I should erase this. Not that it's, the expression's not wrong, but it's good to put some additional details here. So it depends on rho, and it depends on measurement of A1 all the way to AN. So we should make that explicit. And this will be equal to trace rho pi J1, 1, pi Jn, n. Suppose we want to sum over J1. What I want to show now is just that when you sum over J1, you're going to have that the dependence on A1 disappears completely. And so you have a version of non-signaling that still holds, even if you just have these joint measurements. So sum over J1 of probability J1, Jn, rho, A1, An, equals sum J1, trace, rho, pi J1, 1, pi Jn, n. So the linearity of the trace, I can bring it in. Trace rho sum J1 pi J1 1 pi J2 pi Jn 2n. This, because it's coming from the spectral decomposition, sums to the identity. So we have, this is trace rho pi J2 2 pi Jn n, which is just the same as the probability of if I had marginalized over J1 in this probability distribution. Probability J2, Jn, rho, A2, An. There's no pun intended, there's no trace remaining of A1, so it satisfies this sort of, I still call it non-signaling, but I mean, technically that's not really signaling, right? Because you're not talking about space-like separated parties. These are just sets of commuting observables. So I would say that this is just compatibility and or maybe sometimes people call it non-disturbance. The reason for that, I think, is that you're thinking of, you've done this joint measurement, and what you're kind of saying when you sum over J1 is that having done A1 or not having done A1 or choosing something else here does not disturb the outcomes of the remaining measurement statistics. So in some sense, that's kind of what non-signaling is telling you. It didn't matter what Alice or Bob did, just that whatever Alice or Bob did didn't affect the other. So here, it's as if saying that including a certain measurement in your set of commuting observables or not, so long as they were commuting, does not actually change the measurement statistics. So I've seen people say non-disturbance before. So quantum mechanics maintains a notion of non-signaling even for general sets of commuting variables. And so we want to actually formalize this more broadly in terms of just, I have a set of measurements, like my A1 to AN, and I can measure some subset of them. I mean, in this case, they're all pairwise. They can all be jointly measured, but I will have a set of measurements, subsets of them that can be measured together, i.e. in the quantum case, that pairwise commute. Those are going to be called a context. And all I'm going to ask is that these different contexts, they agree on their overlap. So if there's another context where A1 is replaced by A1 prime, but it still commutes with the rest of them, I'm going to ask that the probability distributions on their overlap, the A2 to AN, still agree, whether I marginalize with the A1 prime or A1. So that's all I'm going to ask. And then we can basically rerun many of the arguments we did for CHSH, but in this more general scenario. So you can just sort of talk about these non-contextual value assignments or global outcome assignments that we talked about last time. You can define the Bell polytope. You can define a non-signaling polytope, the set of all possible statistics that satisfy some conditions. So we can basically do most of the same stuff, but now it's in a slightly more general setting. And I'll give an example soon. Let's just define a couple of things, and then we'll look at an example that's not of this form. So the formal setup is I want X to be a finite set of measurements. I take O to be finite set of outcomes. I mean, this could be our 0 and 1 or whatever else it might be. So if you have some set U, which is a subset of X, then we call a function from U to O is called a value assignment. And we will sometimes use this notation that the set of all, so this is an S, sorry, S. The set of all functions from U to O is going to be U, sorry, the other way around. So this notation will be used for the set of all value assignments because the idea is that, if I think of this as being like an outcome 0 or 1, 2 to the U is kind of like the number of possible assignments that I could give to all the measurements here. So I don't know if that's a standard notation, but by the way, I should mention that a lot of what I'm writing down is going to be based off of, not exactly, but morally, a lot of what I'm writing is from Abramsky and Brandenburger. They have a very nice paper called The Sheaf Theoretic Approach to Non-Locality and Contextuality, or something along those lines. So a context. So subset C, I will try to distinguish C subset of X is a subset of jointly of, measurements can be performed jointly So a subset of measurements that can be performed jointly is called a context. And so these are precisely the things that will show up in an empirical setting. These are the analog or the more formal version of just the subsets of my measurements that pairwise commute in the quantum setting. And the outcome assignments on C are precisely O to the C. And these are precisely the ones that we'll be able to see in an actual empirical setting. So these are all the outcomes that we assign from C to O. Let's see, there's a couple of things more I want to say here. Let's see if I can fit it in here just a little bit. I want to say that the set of all context this is my curly C, and I just want to say that there's a couple of things that we're just going to assume. There's no major loss of generality in doing this, and I'll explain why. One is that if I take the union of all contexts should equal my set of measurements. And I have that C are maximal. Okay, so let's unpack this. I'll start with the second one first. C are maximal. So I have my set of possible contexts. All contexts in here are maximal in the sense that if there's another C prime that's a subset of C that's inside of here, then it means that C prime equals C. The point is, I don't want contexts in here that are just subsets of ones that I already have. This is not interesting to me because when I have a situation like that, I can always get the subcontext by marginalizing over one of the variables. So if I include a context where there's a subset, this is not giving me any new information. I could have already gotten the probabilities on that subset just from the bigger one. So it's not that interesting. Also, I want the context to cover my set of measurements. Suppose that they didn't. There would be some isolated or some set of measurements that are not in any context at all. If a measurement's not in a context, it's not really that interesting. It's technically will be a different sort of empirical model. But it won't be really interesting. It'll just give some probability distribution on one measurement, and it will not really affect our analysis of contextuality at all. If I just have some isolated measurement, it doesn't change whether a scenario is contextual or non-contextual. It doesn't really add anything to the analysis. So we just want to make sure that we only are keeping the interesting contexts. Okay, very good. Okay, so what do we mean by an empirical model? The idea is that you have contexts, and for each of these contexts, you define a probability distribution from O of C to, so PC of, so for all maps in here, which we'll call S, it's greater than 0, and S in OC, PC of S. So for each context, you have something, a probability distribution over the possible outcomes, which are non-negative, normalized, and we require or compatibility in the sense that suppose you had, so if you have two contexts, C and C prime, this is their intersection. And suppose you have some value that you define on their intersection. So let's see if I don't mess up the notation here. So I'm defining a value on their intersection. Basically, the analog of this is that C intersection C prime is like Alice or Bob on their own particular site. And now I'm picking some value for that intersection, just 0 or 1 for either Alice or Bob at their local site. And I'm just going to do this. I'm going to write this down. It's going to look a little bit messy, but hopefully it will be clear when I sort of explain what's going on here. Because we sort of have the intuition of what this should look like, non-signaling means that when I sum over all the value, all the possible outcomes associated with the full context, such that S restricted to their intersection equals to R, PC of R equals sum S prime such that S prime restricted to C also equals R of PC prime of R. So here on the left-hand side, I have that C intersection C prime is just some measurement or set of measurements that are only in this context, or that are in the intersection. And then I'm summing over all the possible outcomes that are consistent with R. And these will, in general, not depend on whether I summed over C prime or summed over C. Let's see, I want to make sure I didn't skip something here.
So this is, I mean, so these are basically the restriction maps.
Yes, that's right, but you know, it's not clear if one should really include all of that mathematical sort of notation, but it's exactly like this. Yeah. Exactly. I mean, you could say something along the lines of you have some empirical model and you're just saying that PC, the restriction map CC prime equals P C prime restriction to C C prime, something like this. So we have this, the 3 cycle. So in the 3 cycle, we have x1, x2, x3, and we have equals 0, 1. So let's see, we have the set of contexts are going to be equal to, let's see, I call them xij for I less than j equals 1, 2, 3. So here, Cij is xi, xj. So here I just have a set of 3 measurements. In fact, there's going to be a sort of way of representing these things. Each measurement I can take to be a point, a 0 simplex. So x1, x2, x3. The contexts have 2 measurements in them, so I draw a 1 simplex. So the simplices are going to be precisely 1 dimension down. So I have a point. This is a 0 simplex corresponding to a single measurement. If I have 2 measurements, the corresponding simplex that defines my context is a 1 simplex. So if I had 3 measurements in a context, then it would be a 2 simplex, which is the triangle filled in. Note that this is not filled in. And that's important in this case because it's not always the case that you can actually fill this in. It depends on the empirical model. So what do I mean by fill it in? Filling it in would mean that this whole thing could be interpreted as a context. What does that mean? That all 3, you could have a joint distribution over all 3 of these. That's not always possible. And I will give an empirical model. So S 0, 0, 0, 1, 1, 0, 1, 1. So C1, 2, 0, 1 half, 0. C1, 3, C2, 3, 0, 1 half, 1 half, 0, 0, half. Okay, so is this a valid empirical model? So let's check. Non-negative, okay. In this case, what does it mean for non-signaling to hold? It means that if I have C1, 2, and I want to marginalize, say, the intersection of these 2 is the measurement x1. Is the probability of getting a particular outcome for x1 the same in these 2 contexts? Well, what does that mean? Fix one of the values, say 0 for measurement 1, 0, 0. And then you sum over the other one. So you sum 0 plus 1 half. So I get probability of 1 half. Here, I do the same thing. These are my 2 when I fix measurement 1 to be 0, because I'm choosing it to come first. And then I measure, and then I sum over these. 0 plus 1 half equals 1 half. If you look at all the rest of them, they're all non-signaling. But there's something very interesting here, which is it's contextual. And you can see this in the following way. C1, 2, so if I look at this context, the outcomes are such that the outcome of 1 is always opposite the outcome of the other, of the measurement outcome of 2. So because it's either 0, 1 or 1, 0. The outcome of 1 is always opposite 3, right? Because they're 0, 1 and 1, 0. But so then you would expect that if 2 is always the opposite outcome of 1, and 3 is always the opposite outcome of 1, that 2 and 3 need to be the same. But here we see that they're always different. So there's no actual sort of global outcome assignment that you can associate with this empirical model. So here you have a case where it's not possible to think of this distribution as coming from a filled-in 3-simplex. For that, you would need the 1/2 and the 1/2 to be here instead. I should say that this is kind of interesting. You don't get anything interesting for this scenario in quantum mechanics. Can you see that? Because what would that mean? That means that, say I have observables A, B, C. Each of them are pairwise commuting. If they're each pairwise commuting, then they share a common set of eigenvectors. And so I can define a distribution on this scenario, but it will always be equivalent to something coming from a joint distribution. Because, in fact, in the quantum case, because they all commute, I can always fill this in some sense. You could work it, maybe that's, okay, thank you. That's a good homework problem. I will include this in the homework.
So it's neither in quantum mechanics or classical.
So in quantum mechanics, for sure, you don't get anything interesting. This empirical model is just coming from basically abstractly. You can write it down. It satisfies non-signaling. It satisfies all the conditions, but it's not classical. You can't get this not from quantum mechanics, not from, no, it's just a distribution you can write down. Another way of looking at it is you define a non-signaling polytope based off of these conditions. So here you have a table of how many probabilities? 12 probabilities. They're all non-negative, they're normalized, and they satisfy non-signaling. So just like the CHSH, you can define a polytope of all possible non-signaling distributions. This is a vertex of that polytope. So the CHSH can also be CHSH. So the CHSH would, in this case, be something like this. X0, X1, Y0, Y1. You can measure the X's and the Y's together, but never two X's together. And so you have 4 total measurements, and these are precisely the commutation relations that you have in the CHSH scenario. Boop, 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 boop. Actually, you can define the n-cycle scenario as x1, x2, x3. So let's see. X and so you can just sort of think of a single cycle, something maybe like just a graph with a single loop. And so you can define a measurement scenario just like this. When n is equal to 5, you have this KCBS one that we will discuss probably next time. N equals 3 is precisely this. N equals 4 is the CHSH scenario. So this is an example, and this is also not multipartite in the way that you would think about it, because at any given context, you have that each is only talking to its neighbor, not with all of them at once. So one thing to say here is the notation will be a little bit different than our treatment of the CHSH scenario. There I had P tilde and delta tilde to distinguish them as being joint probability distributions. I think I will drop the tildes. Hopefully it's not too confusing. So a global value assignment is S from X to O, or just S is an element of O to the X. So I take every measurement, for example, in the CHSH scenario, and I assign a value to it at the same time. And for each S, we can define some delta S of S prime, which is 1 if S is equal to S prime and 0 otherwise. So this is analogous to these tildes that we were talking about last time. And in particular, I think we can emphasize a certain point, which is that these S's are coming from a joint distribution. And because of that, these are going to have a product structure. So for a global assignment, say we take S in OX, I want to write S as a tuple of numbers, S of X for X in X. Just, I'm going to write their images like this, so that this guy is going to look precisely like delta S of S prime is going to be a product of X in capital X, where these are delta functions on each individual outcome. S prime of X, S of X. So in some sense, it's worth pointing out that the non-signaling conditions will also hold many of the sort of previous things that we wrote down. You will see that if I take a sum over some subset of these, it will satisfy non-signaling, because if I sum over certain measurements, then in addition to, so when I sum over some measurements in this set, I will get rid of some of these delta functions, and the left-hand side will no longer care about those measurements at all. And in that sense, they are going to be non-signaling. So suppose we have a global assignment like this. This gives us an assignment on all subsets. Then for all subsets U of X, I have U, what I'm going to call U restricted, S restricted to U, which is an element of all the outcomes on the set U. So let's see what this looks like in an example. Say that I have x equals x, y, z, and O equals 0, 1. Then let's take S in O of x to be written as a tuple like this. S of x, S of y, S of z. Sorry, this is S equals, and say that this is like 0, 1, 0. Well, if I have some subset U equals x, y, then I have that S restricted to U is just going to be my tuple given by S of x and S of y. So, which is just to say that if I have some global assignment, I have assignments on all the subsets, including the contexts. So which is going to amount to saying that if I have a global value assignment in the corresponding distribution, then by marginalization, I will actually get a deterministic assignment on a subset of the measurements, precisely those that are consistent with S. So those that are coming from S restricted to that subset. Okay, I think that we're almost out of time here. So did they lock the... We're the last one, right? Did they lock the door or something? No, okay. So what it means for the values to be... I should add a little bit of a comment here. So the fact that this global assignment maps to assignments on the subsets is what it means to have a predetermined set of values. So this is a non-contextual value assignment. It determines the outcomes on all the subsets. So when I measure just the subset and I get some outcomes 0, 1, 1, 0, whatever, these were, in some sense, and then I measure a different context and I get some different values. These are predetermined in the sense that there was a global S which determined those properties prior to any context being measured at all. So we can define a deterministic empirical model. And that's going to be like this. So let's fix a context C in some outcome R. So this is what you would observe in some actual part of the experiment when you measure the observables in the context C. Then we say D of S restricted to C. So I'll try and of R is defined as summing over all S prime, all possible joint global value assignments such that their restriction to C is equal to R. Delta of S prime. And this is precisely the product of deltas, X and C, delta R of X, S of x. I should maybe unpack this a little bit. This is similar to what we did last time, but the idea is that I can define a probability distribution on a particular context just by marginalizing over all of the assignments that agree on that context with some outcome R. And this is just a product of deltas. So if I start with some delta on each context, I'm going to get a product of deltas, just as we did before. And so it'll be, we can just say that the deterministic, okay, so we'll call a deterministic empirical model is going to be just a collection of probabilities like so D of S restricted to C of R over all R in OC and all C. So what is this saying? Basically, all I'm saying here is that I have a table of probabilities that are deterministic, and I have them for each possible C in my set. Let's see. You have 5 more minutes? Okay, so because this is the last part, might as well just finish it off. It will be awkward to include it in the beginning of next time. So how about a general classical probability? So if we have a general joint probability distribution, then I used this trick last time, P of S prime. This is a global outcome assignment, is equal to the sum S over OX of P of S delta S S prime. Just writing it as a convex mixture over my delta distributions. The corresponding empirical model, PC, for some R, is going to be given by marginalizing, again, just as we did here, over for some outcome R on this context C, we're going to sum over S prime in, sorry, let's make sure, S prime in OX such that S prime restricted to R equals C of P of S prime. Now I will use this trick. S prime OX S prime of so this one will be S of O of X, P of S, delta S, S prime. I'm going to rearrange the order of things. And basically what I want to do is take this out front. The only thing that depends on S is, well, no, it's not the only thing. But the only thing that depends on S prime is this. And this is precisely the formula that we already wrote down here for this. So we're going to have sum S of O of X, P of S, some S prime of O of X, but only on a subset, those such that S prime reduced to C equals R of a delta Now this is precisely this guy right here. So I have that this is P of S, ds restricted to C of S. Oh, of R, sorry. And this is precisely what we will define to be P of C. So then we have that the empirical model for the whole thing, I will call it PE, is going to be given by all those PC of R and C and C. So this is the corresponding empirical model. In particular, I can think of this thing, PE, as being, because this is just an average over the probability of my global value assignments, I can think of this as an average over these, my deterministic distributions. And we will call any empirical model that's of this form, we're going to call this thing classical. When it's a multipartite situation, you call it local, otherwise non-contextual or classical. And I want to say one last thing. Erase this. So there's a couple of sort of punchlines here. You have that sorry, global probability joint distribution is true if and only if you have a, so because I can sort of consider these things to be hidden variables, I have this global joint probability distribution if and only if non-contextual hidden variable model. Also, we can define, as we did with the Bell polytope, the classical polytope. This thing is the convex hull of ds. So then you have the following things that are sort of equivalent is so an empirical model is classical if and only if PE is in here, which is true if and only if there exists a global joint distribution, which is true if and only if there's a non-contextual hidden variable model. So we have just all of these different notions of classical, which sort of emerge. You have this geometric point of view, you have this probabilistic point of view, you have the physical point of view, and this is what we mean by saying a distribution is classical. Okay, and that's it. Sorry, thank you for sort of staying a little extra.